Welcome to your own channel of Right Funda.
There is a very interesting problem from magnetics, that is magnetic effect of current. In fact, this is a previous IIT JEE problem, JEE Advanced. So let's go by the proper wording of the questions. What it says. A ring of radius capital R having uniformly distributed charge capital Q is mounted on a rod suspended by two identical strings. The tension of the strings in equilibrium is T naught. Now a vertical magnetic field is switched on and the ring is rotated at constant angular velocity omega. These are the data is given, and what the question asking? Find the maximum omega with which the ring can be rotated if the strings can withstand a maximum tension of 3 T naught by 2. So this is a rod. Over this, there is a ring has been mounted. If the ring has been mounted, there must be some spokes, massless spokes will be there, something like this. I'm having some spokes are there. Okay, and this ring is there, and this is suspended by two threads here. And the mass of the ring, mass of the rod is not given. Rather, what is given? The tension is given. So indirectly, we can find the mass of the system anyhow. And initially, the things were there, and there is a magnetic field, and we're not rotating earlier. So it is not rotating. This axial system must be there. So it is not rotating. So at that time tension was T naught. But when you start giving some angular velocity to this, then what is saying that what maximum angular velocity can be given to this so that the strings will not break. What is given? The breaking strength, or the maximum tension what the string can be in is 3 T naught by 2, where T naught is the tension in each string when it was not rotating, and the distance between these two suspension point of suspension also given to us. So now you have understood the question. So now you give it fair trial of solving the problem. You wish you can pause the video and solve it yourself, and in case you are not able to solve, or you can able to solve, after that you can again resume the video and you can go through the solution that I'll be discussing right now. So let's discuss what is happening right now. Okay. So if I draw the free body diagram of the block, the free body diagram of the block will be like this. Suppose there's a ring there and this there. I don't know, but the mass of the thing is not given. Suppose the mass of the ring plus the disc with the spokes is equal to mg. Okay. And this two tensions will be there. So suppose I take this the x-axis, this is the y-axis. So automatically right-hand coded system I'm doing. Then the coming out, this will be my k cap axis. Coming out of the screen will be my k cap. I cap plus j cap will be k cap. Anyhow. So here there will be two tensions will be there, and I can write here equal tension equal T naught equal tension equal T naught. How I can say tension equal T naught? These tensions should be same because the net torque also should be 0. Net force also should be 0. Net torque to be 0. About this point I will take the torque when both the tensions should have the equal torque, and that equidistance points are there. So this distance are equal. So these forces must be equal to cancel the torque. One is producing clockwise torque, another is covering the anti-clockwise torque. Mg is not producing torque about this point, and net torque is 0. So both the tensions are same. So if this system was in equilibrium, if the system was equilibrium, then what I can write is the net force must be 0 and net torque must be 0. Net torque must be 0 I have considered. That's why both the tensions are same. If I write what are the forces acting? T naught upward, and mg downward. T naught j cap plus T naught j cap plus mg minus j cap 0. Or from this I got the equation 2 T naught is equal to mg. 2 T naught. The mass was not given, but I got the mass value from this as the 2 T naught is equal to mg. This I obtained from this. Okay. So we got a 2 T naught equal to mg. Now this ring is rotated. If this ring is rotated right now with the angular velocity omega, then what will happen? We'll see. Again, we'll draw the free body diagram. Then this is the situation here. Again, will be equal to mg will be there. Tensions. Now the tensions no longer will be same. Will be same. Why? That not be same. Suppose I give the name of this equal to T1, and this I given the name of T2. Two name I've given. Tensions are T1 and T2. And this you will see this is a current carrying loop. Why? Because charge particle is there and charge particle is revolving. So the whole charge is moving like this, circulating charge, and there's a current there. So if a current carrying loop is there, then it will have some magnetic moment like this. And this magnetic moment right now placed in a uniform magnetic field, it will be experienced in torque. and is the M cross B, then torque will be saying that it will be experiencing a torque. Let's calculate the torque and discuss why T1, T2 will be different. So if the torque will say tau is equal to M cross B. Here M is in the I cap direction, B in the J cap direction, we'll see. And M cross B, I cap cross J cap is equal to K cap. So I put this equal to tau magnetic torque. The torque due to the magnetic force, that will be equal to M cap direction. What do you make K cap directions? This torque direction, this axis of the torque will be like this, coming out of this screen. Key cap directions, the torque directions. So it has a rotating tendency. Axis is like this, means what? If it's the right hand you use, then you will come to know it has a rotating tendency like this. This will try to rotate the system, that the rod system in this direction will have rotating tendency like this. So this rod try to rotate like this. So what will happen right now is that this point try to go up and this point will try to go down. This will try to go up and this will try to go down. So, but this is connected to a thread here. So this length cannot increase. This length is fixed. So this cannot go down. If it goes down, then only it will be tilted. So if it is not going down, it cannot be tilted also. So what happens? This value become lesser than the previous value, but this value become more than the previous value. This value may be equal to 0 also. We don't know how much lose is there, but we'll be calculating what the T1 and T2 will be there. So if I total tendency, but right now also what happened? For the system to be in equilibrium, net force has to be 0 and net torque has to be equal to 0. So we'll see what the torque they will be producing and what the force are there. We see that there are definitely T1 is acting upward and T2 acting upward. So T1 plus T2 must be balancing mg right now also. And if you see the torque equation, right, d by 2 into T1 k cap, d by 2 into T1 k cap plus d by 2 into T2 minus k cap. Here this is a d by 2, this one. I cap cross j cap is equal to k cap. This also will try to rotate like this, and this torque will be rotating like this. So this torque plus this torque must be balancing this torque. The tension will be, has to be more than that, so that it can balance the torque due to both torque due to magnetic force as well as for the torque due to tension. The right hand side T1 will be there. So from this we can calculate this. We can simplify this one, and we can get the equations. That people say here, one confusion people say also thinks also that about which point you are taking torque. We are taking the torque, we have written the torque about this point, about the center of mass of the system, rod ring system. This is center of mass here. So mg is passing through this point. And but people say that about this, what is this M cross P? Tau is equal to M cross P there. This is about which axis? Yes, this is the torque. When a magnetic moment is magnetic dipole is placed in a uniform magnetic field, it expresses a torque. The direction is given by perpendicular to both M and B both, and it is given the right hand thumb rule. And the axis has to pass through the center of mass of the system, because center of mass has to be rest. Of the net force on the ring is equal to 0. So center of mass has to be at rest. So it passes through the center of mass. But where exactly this torque? The torque does not act at this point. Torque and everywhere torque act. Everywhere, this side, this side, torque act everywhere. So that's why the torque is not passing to this point. But mathematically we think that axis has to pass through this point. The torque axis has to pass through this point, but torque won't pass through this point. Torque will be in all the directions. So there, that their torque is not 0, but mg's torque is 0. Or again, the component of the mg's torque in the direction of k cap is equal to 0. So T1 contributes to the torque about this axis, right? Rotating tendency like this, rotating tendency like this, or this magnetic torque or torque due to magnetic force also will be about that axis. So this all the torque are there, and we will simplify the equations, and we can get T2 take upon D2 into T2 minus T1 is equal to MP. D2 into T2 minus T1 is equal to MP. And these two equations are there. And from this we can get T2 minus T1 equal to MP T. So I call this the equation number 1. I call suppose this equation number 2. If I simplify this two equation, if I add both the equations, then I can get T1 will get cancelled. T2 and T2 will be added together, and we can obtain the equations that 2T2 will be equal to mg plus 2mb by d. These two equations are adding. Or, but mg, what is mg? We'll see. We calculated in equilibrium condition the mass is equal to 2t naught. So mg, m is small mg, not given the question. So if I put the value of mg, then I got that 2t2 is equal to 2t naught plus 2mb by this. I can cancel this one, this, and this get cancelled, and we remain with, we can calculate the value of T2, the increased value of T2, that will be T naught plus something that we obtained. T naught was their tension, but T naught plus mb by d, where m is the magnetic moment of the ring due to its spinning about the one axis, and the B is the magnetic field in which it is placed, D the distance separated between two point of suspension. We got the T2 we obtained. Similarly, we could have calculated T1 also. We can calculate about this, substituting the value of T2, we can calculate in this any of the equation, we could have calculated the value of T1 also. Now, if you see this, what the question is given, that this is increased tension. As you keep on giving the rotation, more and more spinning will be giving. The more and more spinning will be that the T2 will keep on increasing. But the string can withstand a maximum tension of 3 T0 by 2, not more than that. So as you keep on increasing the omega, and the magnetic moment will keep on increasing, the current will keep on increasing, the magnetic moment will keep on increasing, that T2 will be keep on increasing. So but T2 should not be exceeding before the tension at which it breaks. So if you see this one, this T2 has to be less than equal to 3 T0 by 2, which is given the question is the breaking tension at which it breaks, 3 T0 by 2. So if I put these values, then I can simplify this equation. In place of T2, what I obtain T0 plus mb by d, I'll substitute. This will be like this. T0 I have to put to that side, then equal to mb by d should be less than equal to T0 by 2. For m, magnetic moment due to the spinning of the revolution of the ring should be, m should be less than T0 d by 2 t. Now we'll calculate what is the magnetic moment in there. Let's calculate the value of the magnetic moment. Okay. So once you get the value of magnetic moment, you can substitute. Suppose this is my ring. Suppose the ring is rotating like this, spinning like this. If I having charge is there, there is a charge is there, Q charge is there, and this charge is there. I observe any cross section I observe here. Then if it's complete one revolution, when it complete one revolution, then whole of the charge pass through this point, and current is the charge crossing any cross section area. So if it is one rotation, then the Q charge pass through this one. So the current is the how much charge pass through in 1 second. Suppose it is having a frequency f frequency, f revolution per second, the whole charge is passing through this point in f times. Whole charge Q is passing f times, so Q is equal to f this. Or I can write the Q is equal to frequency nothing but the omega by 2 pi. So I know the current is equal to Q omega by 2 pi. If the Q is the charge in the ring, omega is the angular frequency of revolution there. And I can calculate the magnetic moment. If a current carrying loop is there, it is having magnetic moment, and the magnetic moment is given by this current into area of cross section of the loop. Area of cross section is the vector quantity, but I have taken the magnitude, m magnitude equal to I into area. If I substitute the value of I is equal to Q omega by 2 pi, what I calculated here, and the area of cross section of the ring, this radius is given to r, so this is equal to pi r square is the area of cross section. So I can calculate the magnetic moment to be equal to r Q omega by 2 pi into pi r square. I can cancel this pi and pi, this pi get cancelled, and what we remain with the magnetic moment is equal to Q omega r square by 2 that we obtain. And this value will take and substitute here, this what magnetic moment we obtain, this value will take and substitute here what we got, the inequality where the magnetic moment should be less than this, and magnetic moment is a function of omega. This value will substitute here, m is less than equal to t d by 2b, that will substitute, then I can get this equation. This is the magnetic moment I obtain, and this m should be less than equal to this that we have obtained here. So if I substitute this one, from that I can simplify, I can get the omega, that omega should be less than equal to Td by 2b r square. So maximum angular frequency that can be given to this, because beyond this angular frequency will be giving, the magnetic moment will keep on increasing, magnetic moment will keep on increasing, then the torque on the that ring or the system will keep on increasing. More the torque is there to keep it in equilibrium, this has to be more and more. Otherwise, if the torque is there, start rotating, this has to break. This has to break because it has to go to down point. So T2 is increasing, T2's maximum value this much. So without breaking the system, we can give a maximum angular velocity of T0, D, T0 the breaking strength, D the distance separated to point of suspension, Q the charge in the ring, B the uniform magnetic field that is acting in the upward direction, R the radius of the ring that can be given to the system, so that this will remain in equilibrium. This is a very nice question. Hope you have enjoyed the solution.